So when we're using implicit differentiation to find dy dx, we're making the implicit assumption that y is a function of x. So if I differentiate both sides here, the derivative of x cubed is 3x squared. The derivative of y to the fourth is going to be 4 times y cubed times dy dx. It's kind of like you have a function to the fourth power, and the derivative of some stuff to the fourth is 4 times your stuff cubed, and then you have to use the chain rule multiplied by the derivative of your stuff. On the right-hand side, we have to use the product rule. The derivative of x squared is 2x, leave the y alone, add, and then switch it up, so leave the x squared alone, and multiply by the derivative of y, which is dy dx. The rest of this is not that important. The rest of it's just algebra. So you bring all your dy dx's to one side. I bring them all to the left. So I'd have 4y cubed times dy dx minus x squared times dy dx equal to 2xy minus 3x squared. And then factor out dy dx from the left. So you have a dy dx times 4y cubed minus x squared equal to the same thing on the right. And then finally divide by that to get dy dx by itself. So you get dy dx equal to 2xy minus 3x squared over 4y cubed minus x squared. Really the point of this, though, was that you can be reminded that when you differentiate something like this, you have to multiply by dy dx when you differentiate y to the fourth. You get 4y cubed times dy dx. Similarly here, when you differentiate y, you get dy dx, the derivative of y with respect to x. Cool. As usual, I'll remind you, you're always welcome to ask questions. Don't hesitate. Those of you on Zoom as well, you're welcome to type something in the chat or unmute yourself and say words. So let's talk about solving some differential equations that are not separable. And we're just going to start with an example, and then we'll move on to talk about kind of where it all comes from. But I think it's good to do this as an example first. So let's say we want to solve the following differential equation. Solve y prime or dy dx, either way you want to write it, plus 3y equal to just good old t. Now I'll point out this differential equation is not separable. So this diff EQ is not separable. If we were to isolate y prime or dy, is she using x or t, by the way? Like, I mean, or it'd be both, right? Use both? Okay, great. Typically, the independent variable is either x or t. It really could be anything, though. So here, I would point out, if you tried to isolate y prime, right, y prime equal to t minus 3y, or dy dt equal to t minus 3y. This right-hand side cannot be expressed as something with just t's and something with just y's. So it's definitely not separable. So when we have a differential equation and it's not separable, the only other method that we're going to talk about is what's called using an integrating factor for a first order linear differential equation. So the first step here is going to be to find the integrating. Actually, the very first step is to make sure it's written in the appropriate format. So it should be written as y prime plus a function of either x or t or whatever your independent variable is times y equal to some other function of your independent. So you want to make sure it's written that way. If it's not written that way, you're going to manipulate it until it is. After that, and so we have it here, right? In this case, so for our function, for us, our p of t is equal to just 3, and our q of t is equal to t. And then after that, we're going to find the integrating factor, which some people like to call I and some people like to call mu. It sounds like she is using I, so I will use I. So we're going to say that I of t is the function of t is going to be equal to e to the integral of p of t dt. There is a reason we're doing this. We'll explain in a little bit here. For now, let's just do it and we'll see where we get. So in this case, our p of t is just 3. So our I of t is going to equal e to the integral of 3 dt. The integral of 3 is 3t. So I'm going to get 3e to the 3t. I'm not worrying or concerning myself with a plus c here. You do not need it. We ignore it completely. So that integral up there, you don't have e to the 3t plus c. You just have e to the 3t. Okay. And then I'm imagining, because I know Dr. Burke somewhat well, she's not just letting you jump to the end. She wants you to show the steps in between, probably, at least the first few times. So the next step is then to multiply both sides of the original equation by our integrating factor. So we're going to multiply both sides of the equation by the integrating factor. And sure. So I'm going to say that I have e to the 3t times y prime plus e to the 3t times 3 times y equal to e to the 3t times t. And probably the easiest way of doing this next part is just going to be having you do it. So here's what I want you all to do. For this next part, before we get to the fourth step, we're going to take a quick journey. I want you all to use implicit differentiation, to use implicit one more time, to take the derivative of y times e to the 3t with respect to the variable t. So in other words, you're going to find the derivative of y times e to the 3t, and yes, you need to use the product rule. Okay. So what do we get? So the derivative of y times e to the 3t. So using the product rule, first we're going to get the derivative of y, which is just dy dt, or y prime if you prefer, times e to the 3t, plus, then we switch it up. We leave y alone. We multiply by the derivative of e to the 3t, which is e to the 3t times the derivative of 3t. And here's what we all want to see. The derivative of this is exactly the left-hand side of this equation. I've written it maybe in a slightly different order, but this is exactly the same as y prime times e to the 3t plus y times e to the 3t times 3. And that's the kind of the point, actually, is that after you've multiplied both sides by this I integrating factor, the left-hand side is always exactly going to be the derivative of a product like this. Here's a fun fact. The product that is always going to be the derivative of is going to be, we have a different color pen here, is going to be, drumroll please, it's always going to be y times your integrating factor every single time. The trick I've developed for myself is when I look at this, I just look at the thing that has y prime and I drop the prime. E to the 3t times y is exactly what we're taking the derivative there. So step 4 is to rewrite this. Rewrite so that the left-hand side is the derivative of a product. Actually, not just any product, of the product, y times your integrating factor. So I'm going to rewrite this as y times e to the 3t prime, or you can put derivative in front of that if you want to. I would just rather use the prime notation, equal to the same thing on the right, which is, I'm going to rewrite the order here just because it feels more natural to write it as t times e to the 3t. Okay, remember our goal? Actually, we didn't even really state our goal, but whenever you're solving a differential equation, the goal is to find y as a function of t. To be able to isolate y here, we have to get rid of this derivative. So we have to anti-differentiate both sides. So step 5, anti-differentiate. Both sides. The antiderivative of the derivative is just the function. On the left-hand side, you're going to get y times e to the 3t. On the right-hand side, we are going to have to actually take the antiderivative of t e to the 3t. That sometimes is difficult. This one's actually going to be a little bit difficult. We are going to do it. And then I'll say, so what I should point out here is that then we'll jump to the solution without finding the antiderivative just yet. But I will point out that people often write a formula for the solution. Finally, the solution is going to be, well, if we divide both sides by the integrating factor here, we're going to get y equal to 1 divided by the integrating factor times the integral of our original function q times the integrating factor. That's what so some professors are totally cool with students being like, oh yeah, you can memorize this formula. Some professors, and I believe Dr. Burke is in this boat, but I don't actually know. Some people want you to show these steps where you write both sides and then you say that the left-hand side is the derivative of the thing and so on and so on and so on. So that's the way I'm going to show it to you because it's good to see that. So in this particular case, we're going to say that for our solution, y is going to equal 1 divided by e to the 3t times the integral of t times e to the 3t dt. Don't be silly like I was when I was a student. Those e to the 3t's do not cancel out. We have to integrate this before we can start even think about canceling anything. So let's integrate it. It's not too terrible. It does require integration by parts though. So for the integral of t e to the 3t dt, we're going to let u equal t. Our du is 1 times dt. dv has to be the rest, which is the e to the 3t times dt. And the antiderivative of e to the 3t is e to the 3t divided by 3. So then this ends up equaling u times v. So t times e to the 3t divided by 3 minus the integral of v du, which is e to the 3t divided by 3 times 1 times dt. I'll remind you, I know it's probably been a little while, the whole point of integration by parts is to get a new integral that's easier to integrate. So this new integral here, the integral of e to the 3t divided by 3 is very straightforward. It's just going to be e to the 3t divided by 3 times another 3. So we're going to end up getting t times e to the 3t over 3 minus e to the 3t over 3 times 3. So here's what our solution looks like. So then looking at this here, our solution is going to be y equal to 1 over e to the 3t times the integral we just found, which is, I'm going to write this as 1/3 t e to the 3t minus 1/9 e to the 3t plus c. And that c, it is absolutely vital that that c is getting multiplied by the 1 over e to the 3t, or the 1 over your integrating factor here. It is required, it is necessary, it is super, super important. You can leave it like this. I personally end up choosing to typically multiply it through. So if you multiply this 1 over e to the 3t through, your e to the 3t's are going to actually cancel out. So we're going to get y equal to 1/3 times t minus 1/9 times 1 plus c divided by e to the 3t. And that is our general solution. You can write it either way. I always like doing it this way because you often see a lot of things cancel out, but either way is totally fine. So this is the process for solving a first order linear differential equation using an integrating factor. Sure. So when we integrate this, I'm really thinking of the integral of e to the 3t over 3 as 1/3 times the integral of e to the 3t. And then when we integrate or antidifferentiate e to the 3t, it ends up being e to the 3t divided by another 3. And the reason for that is really what we're doing here is we're doing a u sub without actually showing the work. But if you think about taking the derivative, what's the derivative of e to the 3t? Sorry, you can't really see that very well. All this. The derivative of e to the 3t is e to the 3t times 3. So the antiderivative has to be e to the 3t divided by 3, so that when we take the derivative, those 3's cancel out. Yeah. How you find the integrating factor? Yes. So whenever we're finding, so in fact, let's do another problem. Let's look at, yeah, here's the one. So let's look at the following situation. So we have, I'm going to use x's this time. X times y prime minus 4y equal to x to the 6th times e to the x squared. I'll again point out, so usually if it's written in this way, we see like a y prime and a y, they're usually trying to lead you down the path of using an integrating factor with a first order linear. Sometimes you could still rewrite it in a way so you can separate, but I don't want to do that here. I know it's not going to be simple. You could try, but it won't work. So I need to first write this in the standard way. So I need to write this as y prime plus some function of x times y equal to some other function of x. And currently, it's not written that way. I don't have just y prime by itself. So what am I going to do to both sides of this equation to get y prime by itself? I've got x times y prime. How do I get rid of the x? Divide by x. I'm going to divide everything by x. And then I'm going to have y prime minus 4 over x times y equal to x to the 5th times e to the x squared. It's not really. So when you divide a product by something, you only divide one of the factors by it. Let me show you what I mean by that. If I said like, and this is going to be kind of a silly example, but like, sure. Sorry, I'm trying to do, yeah. 4 times 10. If I divide both sides by 2, I don't divide each part by 2, right? Because 4 times 10 is 40, and what's 40 divided by 2? 20. But if I divide each thing by 2, I would have 2 times 5, which isn't 20. That's 10. So when you divide a product by a number, you pick which factor you're going to divide by and do just that. So what I'm really doing over here with this x to the 6th, was it x to the 6th? Yeah, times e to the x squared divided by x. I'm saying, oh, x to the 6th divided by x is x to the 5th, and the e to the x squared is unscathed. So now we've got this written in the standard kind of way, and I can see that my q of x is x to the 5th e to the x squared. And what's my p of x? What's the coefficient of y? You're almost correct. It's actually -4x. And here's why. we always have to write this as y prime plus some function of x times y. So I have to think of this as y prime plus negative 4 over x times y equal to x to the 5th e to the x squared. And it is really important that you capture that negative if it's there. So there's our p of x, negative 4 over x. There's our q of x. So the way we find the integrating factor I of x is always going to be equal to e to the integral of p of x. Excuse me. Every single time. That's why we have to identify what p of x is. In this case, it's going to be e to the integral of negative 4 over x dx, which is going to be e to the, let's see, the antiderivative of negative 4 over x is negative 4 natural log of, I'm going to not write the absolute value here. It gets ignored. It's kind of like the plus c gets ignored. The absolute value also gets ignored. So you e to the negative 4 natural log of x. And it is almost always in our interest to simplify this as much as possible. Specifically here, this negative 4 can come up as the power of x in the natural log. So we can rewrite this as e to the natural log of x to the negative 4th, which is just x to the negative 4th. There's our integrating factor.
And
like why we're doing this?
just like what the integrating factor does for us.
Cool. Let me show you. So let's, yeah, we'll come back to this. Yeah, no, let's finish this problem first, and then we'll talk about why the integrating factor does what it does. So, but let's actually see the example here. So next step, we're going to multiply both sides by the integrating factor. So I'm going to take my y prime plus negative 4 over x times y equal to x to the 5th e to the x squared. I'm going to multiply both sides of this equation by x to the negative 4th. And yes, it's in my interest to simplify here. It's almost always in this process in your interest to simplify things as you go. So on the left-hand side, I'm going to have y prime times x to the negative 4th plus negative 4 over x is really negative 4 times x to the negative 1. And negative 4 times x to the negative 1 times x to the negative 4th is going to be negative 4 times x to the negative 5th times y. On the right-hand side, the x to the 5th times x to the negative 4th, we can add those powers and just get x to the 1st times e to the x squared. So here's what the integrating factor has achieved for us. Well, here's what I should say. Here's what multiplying both sides of the equation by the integrating factor has achieved for us. It's going to always turn the left-hand side into the derivative of a product. So this left-hand side, we're going to rewrite this as the derivative of the product of y times x to the negative 4th. Let's check that out and make sure that's true. If I use the product rule here, the derivative of y is y prime times you leave the x to the negative 4th alone, plus you switch it up, you leave the y alone, and you multiply by the derivative of x to the negative 4th, which is exactly negative 4 times x to the negative 5th. So that's what doing this is achieving for us. Right-hand side doesn't change. And then to get rid of the derivative on the left-hand side, we're going to anti-differentiate both sides. Or in other words, if the derivative of this is equal to that, then y times x to the negative 4th is equal to the antiderivative of x e to the x squared. This requires a u sub. So for this here, we would do u equal to x squared, du equal to 2x dx, 1/2 du is equal to x dx. So this becomes the integral of x dx is 1/2 du e to the x squared is e to the u, and the integral of e to the u is e to the u. So we get 1/2 e to the u, which is 1/2 e to the x squared. So the antiderivative of x e to the x squared is 1/2 e to the x squared. You can check that by taking the derivative. So then we have y times x to the -4th equal to 1/2 e to the x squared plus c. And then you could divide both sides by x to the -4th, or you could just as easily, or probably more easily, multiply both sides by x to the 4th. So we're going to end up getting that y is equal to x to the 4th times 1/2 e to the x squared plus c. Or I would probably prefer to write it out as 1/2 x to the 4th e to the x squared plus c times x to the 4th. So let's talk a little bit about why this works. It really works because of exactly how we're making up the integrating factor in the first place. So you may or may not want to write this next part down. It's totally fine. But let me just, let's talk very generally for a second here. So generally, if we have y prime plus some function of x times y equal to some other function of x, the integrating factor that we're multiplying both sides by is e to the integral of p of x. Okay, I'm going to ask everybody an important question, which is easy. What's the derivative of e to the x? E to the x. Okay, it's slightly more difficult. What's the derivative of e to the stuff? Like, for example, what's the derivative of e to the x cubed?
E to the stuff times the stuff.
Right, exactly. Okay, we're going to use that in just a second. So I'm going to take this equation and multiply both sides. In fact, I'm going to do it right now, actually. I want to find the derivative of this. What's the derivative of my integrating factor? Well, my integrating factor is e to the stuff. So the derivative is exactly going to be e to the stuff times the derivative of the stuff. What's the derivative of the antiderivative of p of x? P of x. So the integrating factor, oh, look at this. Watch how I write this for a second. This e to the integral of p of x here is just the integrating factor. Right? It's itself. So this ends up being the integrating factor times the derivative of the integral, which is p of x. Please ask for clarification if you want me to, like, I'm happy to explain something more. So I make sure everything's clear before we take the next step. Okay. I'm going to multiply both sides by the integrating factor. I'm going to rewrite this equation as y prime times the integrating factor plus the integrating factor times p of x times y prime times y equal to the integrating factor times q of x. Okay, but I want to point out here that this part right here is exactly that, which is the derivative of the integrating factor. And it always works this way because of how the integrating factor is defined. The integrating factor is literally always going to be e to the integral of p of x, and its derivative is always going to be e to the integral of p of x times p of x. So look what I've got here. I've got y prime times I plus I prime times y. That looks like a product rule derivative to me. And then the right-hand side is I of x times q of x. We rewrite the left-hand side as the derivative of the product y times I of x. I wish I had like a little bit more space on this piece of paper. And then we anti-differentiate both sides. It's right over here, I guess. to get y times I of x equal to the integral of I of x times q of x. And finally, we divide both sides by I of x. So write this up here, I guess, because I would like to keep this on the same page. We get y equal to 1 over the integrating factor times the integral of the integrating factor times the q of x function. And it always works that way. And again, I'll say this just because I used to make this mistake a lot because I was not paying attention. The I of x's do not cancel there. You have to multiply I of x by whatever q of x is, and then integrate that, and then multiply the whole thing by 1 over I of x, which usually doesn't result in cancellation. Hopefully that helps clarify why the process of multiplying by an integrating factor works. Cool. We got time, yeah. Let's see here, let's look at that one. Sure, that one's fine. So one thing I should point out is that sometimes some problems can be solved either way. So for example, following equation, differential equation, y prime minus 3x squared y equal to x squared is certainly written in a way that would lead you to probably use the integrating factor method, because it's already set up with y prime plus a function of x times y equal to a function of x. But this one could also be solved via separation of variables. Let's do it both ways. So let's do it the way that seems like it wants to do it that way first. So method 1. Although I would usually default to separation. I've changed my mind over the years, to be honest. I used to think separation was kind of easier, but sometimes the algebra is actually easier on doing the first order linear differential equation. So it's really kind of a take your pick if you can pick. Most problems you can't. This one's an exception. So let's do it by the integrating factor. So again, let's be careful here. Our integrating factor, I of x, is e to the integral of negative 3x squared dx. Because our p of x, if there's a minus sign there, the p of x has to grab the minus sign. And that's going to be e to the negative x cubed. Technically, you could jump straight to the answer, right? Well, straight to the answer and still have to do some integration. So I just want to point out that I'm going to show the work here, but we could presumably jump to saying that y is equal to 1 over the integrating factor times the integral of the integrating factor times q of x, which in this case would be y equal to 1 over e to the negative x cubed times the integral of e to the negative x cubed times x squared. Sometimes people are like, yeah, you could just, but I don't know. I've always had trouble memorizing things in general. I don't really memorize this formula. I'm just working through it every time. So the steps we're going to take are really multiply both sides by e to the negative x cubed. So we're going to have e to the negative x cubed times y prime minus e to the negative x cubed times 3x squared times y equal to e to the negative x cubed times x squared. And then this left hand. So here's the thing. I don't want to really have to think too hard about what product this is a derivative of. And there's always a shortcut here. The shortcut when I'm looking at this is look at the term that has the y prime. E to the negative x cubed times y prime. Rewrite that, but don't write the prime. So e to the negative x cubed times y, and then put parentheses around that and take the derivative of the entire product. That always works. So then we still have the same thing on the right-hand side, e to the negative x cubed times x squared. And then differentiate both sides to get e to the negative x cubed times y equal to the antiderivative of e to the negative x cubed times x squared. And that's how we get to this step right here. Dividing both sides by e to the negative x cubed gets you exactly y equal to 1 over e to the negative x cubed times all left. Couple things I would do here. Thing 1, I would rewrite this as just e to the x cubed instead of 1 over e to the negative x cubed times the integral of e to the negative x cubed times x squared dx. Hopefully you see that there is a not too terrible u substitution we can do here. In this case, we're going to let u equal the exponent of e, which is negative x cubed. Our du is going to be negative 3x squared dx. We have an x squared dx, so I have to divide both sides by negative 3 here. Say that negative 1/3 times du is equal to x squared times dx. So the integral of e to the negative x cubed times x squared dx ends up becoming the integral of e to the u times negative 1/3 du. And I like to put the negative 1/3 out in front. So that's going to be negative 1/3 e to the u, which is negative 1/3 e to the negative x cubed. So then we end up getting y equal to e to the x cubed times negative 1/3 e to the negative x cubed. And if we forgot the plus c, our answer would be very wrong and boring. So if we forgot the plus c, you would just multiply these together and get an answer of negative 1/3, which doesn't seem like negative 1/3 is the solution to this differential equation. That seems kind of weird. I mean, it technically is, but it's weird. So you need the plus c here, and then if you multiply it out, you get y equal to this times this is just negative 1/3 times e to the 0 plus c e to the x cubed. Oops, sorry, I didn't mean to cross out the x3 there. That's terrible. 10 minutes, all right. Is that clock right? Sorry. This clock is very wrong. Okay, so where are we going to go with this? Well, we're going to do some word problems where you have to set up the differential equation and then solve it. In fact, let me see. I feel like that one's a bit much to start with. Let's go look over here real quick. Sorry, I have one that's. One moment. Go ahead, that's totally fine. Sure. All right, so let's look at this problem here. So let's do the following. Let's assume that the volume of a weather balloon is a function of pressure. We're going to call it x. And the rate of change of the volume is inversely proportional to the volume. Additionally, we're going to have some initial conditions here. V is equal to 40 when x is equal to 10, and V is equal to 30 when x is equal to 15. Yes, there are some units associated with these things, but let's not worry about the units. So, part A, set up the differential equation. Which honestly is, oh, I forgot to do the other half of that problem. I said we were going to do it both ways. Well, we can do it the other way on Monday. This is more important, I think. So, set up a differential equation is usually the hardest part of these kinds of word problems. We actually have to read the thing and be like, okay, what does this actually mean? Well, we've got volume and we've got pressure. So volume and pressure. And we need an equation with the derivative of volume and some other things. So this line here is really what's telling me what's happening. The rate of change of V. Okay, rate of change of V is another way of saying the derivative of V. So we're going to say, great, the rate of change of V, dV dx, is inversely proportional to V itself. So when we say something's proportional to something else, it means it's a multiple of. So we're going to say this is equal to a constant times, I'm going to pick K for my constant, it's pretty typical. It's a multiple of the inverse of V. So not V itself, but 1 over V. That's our setup. This is our differential equation. You've got a function V and one or more of its derivatives. Great. So now we're going to solve this. Solving it's not terrible. We're going to usually end up using separation of variables. So here, if I have dV dx on the left, which side do I want my v's on? Do I want my v's to be on the left or on the right? Yeah, because you always want the d thing to be in the top, not in the bottom. We don't want dx on the left, we want dx over on the right. So we're going to rewrite this as v times dv equal to k times dx. And there were no other x's to bring to the right. Then we're going to anti-differentiate both sides. So we're going to say the antiderivative of v dv equals the antiderivative of k dx. I should mention, we could have put the k on the other side, but I will tell you that usually you want the side with your function, v or y or whatever we're calling it, to be as simple as possible. So I would always default to making as little on the left side as possible, as much on the right side as possible, if it's set up like this. So then we're going to get v squared over 2 equal to kx plus c. And I'm going to try and solve for k and c, but yeah, so let's do that. So there's our general solution, although I didn't actually solve for v yet, that's fine. But now let's solve for our constants, k and c. So what I would do first, so v squared over 2 equal to kx plus c, I'd multiply both sides by 2, which isn't going to look like it actually does anything. I'm going to call this k1 and c1 just so we can keep track here. If I multiply both sides by 2, I get v squared equal to 2 times k1 is a new constant. Let's call it k2. c1 times 2 is a new constant. Let's call it c2. But really, if someone was actually doing this, they'd probably say v squared over 2 equals kx plus c and multiply both sides by 2. V squared equals a constant times 2 is still a constant times 2 is still a constant. They'd probably just write it that way. And now we know that x equals 10 and v equals 40. And we know that x equals 15 and v equals 30. So let's plug those both in to try and solve for c and k. So when I plug in 40 for v, I get 40 squared equal to 10 times k2 plus c2. When I plug in 30 for v, I get 30 squared equal to 15 times k2 plus c2. And there's a really convenient way we can solve this. I see two equations here where c2 has the same coefficient in each equation. I can just subtract these together to eliminate c2. If I subtract these, 40 squared is 1600, 30 squared is 900, 1600 minus 900 is 700, and 10 minus 15 is -5 times k2, and c2 minus c2 is 0. So it looks like k2 is going to be 700 divided by -5, which is really, let's see, divided by 5 is like divided by 10 multiplied by 2, so it's going to be 140, so -140. And then we can go back and plug that into either equation to solve for c2. So I plug this back into this equation because multiplying by 10 is easier than multiplying by 15. I can say that 1600 equals 10 times -140 plus C2, that's negative 1400, added to 1600, it's 3000. So then I can say that V squared is equal to negative 140x plus 3000. And now we come to an interesting little tidbit here. If I want to solve for V as a function of x, if I take the square root of both sides, what should I put in front of the square root? I should put a plus or minus. Right? If you square root both sides, it could be positive or negative. But we know that V is positive, right? If x is 10, V should be positive 40. If x is 15, V should be positive 30. So we can use our initial conditions to tell us which piece of the plus or minus we actually need. So we actually do want that V of x is equal to the positive square root of negative 140x plus 3000. But I could have written the question in a way where when x equals 10, V was negative 40. And when x equals 15, V was negative 30, so that we need to have the negative instead of the positive. So you can get the negative instead of the positive. All right. That's all I got for today.